In Transcarpathian region, floods occur several times a year, and the extreme floods occur periodically each 10–15 years. One of the active flood protection measures to lower water level is using mountain flood control reservoir, which transforms the extreme flood flow to channel forming flow of 10% probability. Mountain flood control reservoir is created by the dam with bottom spillway. The spillway is designed for discharge of channel forming flow, which passes without changing through downstream. In the case of the extreme flood, the part of the river runoff that exceeded the 10% flow is temporarily accumulated in the reservoir. Expected location of the mountain flood control reservoir is the Irshava River of the mountain part of the Tisa River basin. The dam is made of local materials such as gravel pebble soil with impermeable layer. Mountain flood control reservoir leads to the temporarily intensive water level rising and the same intensive falling the water during the extreme flood. This change of the level may reduce the upstream dam slope stability. Assessment of the slope stability under transient condition is an urgent task that will ensure the reliability of flood protection. This problem can be solved by simulating transient seepage by means of finite element method. The purpose of our work is to simulate the possibility of dangerous landslide process of the upstream dam slope during the reservoir operation, and to determine the optimal design of the impermeable structure of the rockfill dam. The two-dimensional model of the dam with the core, and the dam with the screen were used to simulate the reservoir operation. Since the size of the mesh affects the calculation accuracy, the optimal mesh size was accepted by gradually reducing the mesh from 2 meters to 0.5 meters. The mesh size of 1 meter was set as optimal for further simulation. Hydrograph of the flood of 1% probability was taken for simulation. It's equal 181 cubic meters per second. The transformed flood hydrograph was converted into the relationship between the water level and time. And these hydrographs were divided by regular interval every 5 hours, and this function were used to simulate the change of water level in the reservoir. The mechanical properties of the soil for Mov-Coulomb model were obtained as a result of field review and laboratory processing. Volumetric water content function, hydraulic conductivity function, and residual water content was taken from literature source using particle size distribution of soil. Foundation was assumed full saturated. The stability of the upstream dam slope and transient seepage analysis were carried out by using the software Midas GTS NX, which use Darcy's equation to simulate the transient seepage, and two methods of slope stability calculation: the stress analysis method, SAM, determine safety factor for the several circular sliding surfaces using the result of the stress calculation. The stress reduction method, SRM, is based on the gradual decrease in shear stress until the slope reach limit equilibrium state and don't need predetermined sliding surfaces. It was assumed that the dam had already built and initial deformation was finished. The initial water level was set at the level of 1 meter above the base of the dam. The result of calculation is presented on this slide. During the calculation, the location of phreatic surface were determined and pore pressure stress were accounted in slope stability analysis. Water rising is continuous the first 30 hours. Then the higher water level keeps for 10 hours, during which the phreatic surface does not reach the steady state position. There is a dark red line is a steady state position in the dam Velychko. At the 35 hour, the water begins to fall. The direction of water movement changes. Part of the water continue to go downstream. The second part change direction to the upstream slope. We can see the lag time of the phreatic surface is formed due to the low hydraulic conductivity of the core, and pore pressure quickly dumps inside the prism. The location of the impermeable layer near the upstream slope, the dam with screen, significantly affects the pressure gradient during the water level falling, creating the higher pore pressure than in dam with core. Therefore, from the point of view of reliable operation of the reservoir, the impermeable layer should be moved away from the upstream slope to decrease the pressure gradient and fast the pore pressure dumping in the dam prism. On the next slide, it is shown the result of slope stability calculation by stress analysis method for the dam model with core and screen. The safety factor of the upstream slope of the dam at the 0 point, so when reservoir is empty, is equal 1.5, and it is the same for two construction of the dam. After 35 hours of the flood, the water level begins to fall, and the water level in the reservoir falls faster than the phreatic surface in the dam body, and the slope stability decreases, reaching a minimum value at the time of 50 hours, which corresponds to the highest gradient of phreatic surface. The upstream slope of the dam with the screen loses stability faster than the dam with the core, and safety factor reaches the limit value at which the slope is kept stable in 40 hours. At the same time, the dam with the core has a safety margin. Dam stability simulated by SRM demonstrates the similar trend of safety factor changes as the calculation by stress analysis method, with maximum value at the highest water level in the reservoir and the minimum value at the end of the flood, 50 hours. Simulation under transient condition showed that the upstream slope stability depends on the position of the phreatic surface in dam prism. So the construction of the dam with clay core increased the reliability and safety of the structure and ensures the upstream slope stability. The value of the safety factor calculated by different methods, SAM and SRM, under the same condition differ due to the different radius and sliding surface and its location. The value of the safety factor calculating using SAM are lower than calculated by stress reduction method under similar condition. The overestimating safety factor by SRM were obtained, and another scientist that explained sensitive to the nonlinear solution algorithm and it's incapable to determine other failure surface near critical value. So, since the safety factor value defined by SAM lower, they were taken to assess the upstream slope stability. and the construction of the dam with core was obtained as optimal for design mountain flood control reservoir. Thank you very much.